Hello, hello, can you hear me? Hello? Hello, can you hear me?
Sounds a little quiet. We can turn it up here. Test 1, 2. All right, try again.
Hello, can you hear me?
That sounds pretty good to me.
Okay.
Like, I can hear it down here, so it's probably
Okay.
good up there. And for the recording, it'll.
Oh, well, welcome. Is it on? Hello? Hello? Okay, we're on. Yay, okay. Let's start. I can't clap. So it's my pleasure to introduce Professor Feryal Özel today, who will be our colloquium speaker. She's an expert on neutron stars, black holes, accretion disks, plasma physics. List goes on and on. She got her master's at Columbia University, her PhD in astrophysics at Harvard University. She was a Hubble Fellow at the Institute for Advanced Study, Princeton. And then she was an associate professor and associate dean at the University of Arizona. Now she's chair of the School of Physics at the Georgia Institute of Technology. She's a co-I of NICER, founding member of the Event Horizon Telescope, and lead of the Modeling and Analysis Group. She was awarded a Guggenheim Fellow, as a Guggenheim Fellow. She's a Bishop Lecturer, and was awarded the Maria Goeppert Award. I wanted to point out that her recent review article, Masses, Radii, and Equation of State of Neutron Stars, published in 2016, has 1,000 citations. Well, 998, but we can round up. And I like to assign Özel and Saltis 2015, Statistics of Measuring Neutron Star Radii, Assessing a Frequentist and Bayesian Approach when I teach Ops and Stats. So maybe you've heard her name in that context. So, Feryal, today we're going to learn about what we learned about from black hole images.
Can you hear me okay? Yes. Well, thank you, Adam, for that wonderful introduction, and I apologize for all the papers that you've been assigned by him that I had something to do with. But I do love black holes and neutron stars, and I try to understand in my career the processes that happen around them, or general relativistic effects that get imprinted on the observations that we have of them. So I know there are experts right here in your own department. Jason is right there, an Event Horizon Telescope colleague and collaborator. So I know that you've heard at least a little bit about this pretty crazy idea that we could image black holes at the scale of their horizons and use those images to learn something. So what I'm going to do in this talk is introduce you to why we did this experiment, what we saw, and then go in 3 small different directions on what did we use the results for to learn about general relativity, where did we find that our models, all the 20 years of theoretical modeling, did not work, or at least was incomplete, and at the end, tell you a little bit about the recent machine learning efforts to do this imaging a little bit better. And if I don't have time for one of these things, it's totally fine. We can get to as much as we can. Feel free to interrupt with questions, I don't mind, but let's get started on why we're studying black holes in the first place. I know that there are lots of aficionados in this audience, but just as a reminder and a little bit of a background, black holes are everywhere. They seem to be very powerful. They seem to impact how galaxies evolve from a very early stage. We also encounter a lot of different processes of how stars lose mass, how they form an accretion disk, how this hot accretion disk plasma works, and there are a lot of interesting questions that come about. So here is a typical galaxy. We see both stellar mass black holes and black holes at their centers. And here, for your information, are all the scales that we cover, from the scale of the galactic environments, 10 to 100 parsecs. We feed black holes at 100 parsec scale. The accretion disk is about a tenth of a parsec. The event horizon that we're trying to resolve is 10 to the minus 4 of a parsec. And the plasma simulations that we need to actually understand how it works. All the radiation that's generated that reaches our telescopes is on scales of 10 to the minus 11 parsecs. So there is no brute force method that will get you from here is the galaxy, the gas accretes, the accretion disk forms, here are the gyroradius scales of the electrons where processes happen. So we have to do a lot of creative things in order to simulate how this works. This is a typical tool and a typical setup. I'm sure you've heard from Mitch Bagelman here about GRMHD simulations. I'm going to try and avoid acronyms, but this one is super common, so I wanted to introduce it to you. It basically stands for General Relativistic Magnetohydrodynamic Simulations. What this means is that in order to understand how the gas reaches the event horizon of the black hole and disappears in it, we solve a set of equations that are basically mass conservation, momentum conservation, energy conservation, but it's a hot plasma, so the magnetic field also evolves with the gas and implements or interacts with the gas. So we also have to solve the equations for how the magnetic field evolves. That's the magneto part, okay? And we do this in general relativistic spacetimes. That's where the GR comes from. And it's a very useful tool. We typically, since we can't get to the galaxy scales, we set up a torus at some distance from the black hole. These are in gravitational units. And we put it in some sort of equilibrium, thread it with initial magnetic fields, and then let it evolve, okay? When we let it evolve, there are literally thousands of these simulations. This is one from my group recently, where we set it up with that torus. As you can see, turbulence develops, and matter makes its way through a disk. This was a somewhat thin disk, but it could be different heights as well, to the black hole at the center. And it's this turbulent hot gas that emits the photons that we see in our telescopes. Why do we do this? Well, it's a pretty efficient tool. Even though we can't reach the resolutions that we need to understand everything about it, it's a very good tool to study the basic characteristics. We can run sets of simulations for different initial conditions. For example, how was the magnetic field initially? Black hole spins, mass accretion rates, is a lot of gas going in or a little bit of gas going in, depending on how the black hole is being fed. And even then, we need very large large-scale computing resources to run these library of simulations, and we explore what we can trust and what we don't know. For example, in these simulations, we don't a priori calculate how hot the electrons get. We do that after the fact and say, you know, if it's this versus that, how would what I see change? This is just a snapshot from the large suite of GRMHD simulations we ran as part of the Event Horizon Telescope collaboration. And it's there to just show you. We even give names to these things based on the particular magnetic field configurations that we explore and how they develop. We call some of them sane. We call some of them mad. A is the black hole spin parameter. They could be spinning fast or not spinning at all. And we end up with movies and snapshots of the accretion flow, which we can then use to say, okay, what's the radiation I see from this? Okay? To do that last step, we also use general relativistic ray tracing and radiative transfer simulations. So this is some excellent early work from Jason Dexter, who developed some techniques to ray trace and integrate the little bits of radiation that comes from this gas through the accretion flow out to an observer at infinity. That's this, like, think of this as the observer screen or the telescope. And given a wavelength of light, we could ask, what would this look like? Okay, so around 2012, 2013, we developed new ways of calculating this based on GPUs. We even actually built a GPU cluster so that we could do this efficiently. And for those simulations that I discussed, ask ourselves, what would this look like? Okay? So that's that step. And I will jump to a very recent compilation of these. This was put together by my former PhD student, Leah Medeiros, who took this large simulation library, did radiative transfer ray tracing on all of it, and put one of these collages together that span different mass accretion rates, different black hole spins, different assumptions about how this flow started. And you will see that there are a lot of similarities in those little squares, postage stamp collection. And there are some differences. For example, some are thick, that have these larger spirals. Some are thin. You're seeing only a little bit of a crescent. That also has to do with how the observer is viewing the black hole with respect to its spin axis. But in all of them, you see there is a central hole. In just a few cases, it's obscured by the material in front of it, but there is no configuration that we put all the physics that we know and ray trace it at this particular wavelength, which is 230 gigahertz, the frequency, where we don't see a hole in the middle. Okay? So that tells us that there is something very special about the black hole imprinting its characteristics on the surrounding light that we could go out and look for. Okay? Now, I said this is very recent, but the very basics of this we knew 25 years ago. This is my PhD work, actually, way predating the Event Horizon Telescope, and actually led to some of the early ideas that used not the GRMHD simulations, but some analytic modeling, semi-analytic modeling of these flows to ask what would it take to get to the event horizon of a black hole for nearby sources. And in two consecutive papers, I looked at what the emission, what the size of the image would be as a function of frequency, and asked what would it take to get to the Schwarzschild radius, and that turned out to be the millimeter wavelength that we ended up going after. There were already some long baseline interferometric measurements of the size at the time, so we were very motivated by this evolving technology, but it was the first time we put together the models to say, okay, what would it take for us to get all the way down to the horizon instead of just seeing an opaque torus around it. I even did this in the X-rays. There were concepts for an X-ray interferometer at the time called MAXIM. So we identified Sagittarius A star and M87 as the two candidate black holes for which there would be enough brightness, and the sizes in the sky would be the largest. So because if you're trying to image something, obviously you want as much detail as possible. So you want to look at the biggest possible candidate, which is a combination of how big it is intrinsically and how close it is. So that's where we identified Sag A star and M87, these two black holes you've probably heard of as the two targets. Now, when I say we found the optimal targets, don't be fooled by this. The angular size in the sky is 50 microarc seconds for the event horizon of these two black holes. That is millionth of a degree. Okay? So nobody in their right mind would say, oh, okay, then let's just build a telescope and go and look at that. Like, that's not a thing. But as I said, some of these interferometric techniques were already being developed, and at this wavelength, we needed an additional push. So jumping forward nearly 20 years, it took about that amount of time to put together a network of telescopes that could observe at the 1.3 millimeter wavelength that we needed. It could get to the resolution that we needed because it turns out to resolve 50 microarc seconds at 1.3 millimeters. You do your usual lambda over d thing, and it turns out the distance that you need is the diameter of the Earth. And the only way to do that is not to build an Earth-sized telescope, but to build the next best thing, which is different antennas that can effectively talk to each other, that can record the signal, and then we combine them afterwards as if they were one signal and measure it. So as of 2018, when a lot of the data that I'm going to show you was taken. These were the telescopes spanning from the South Pole all the way to Greenland, Arizona, Hawaii, Chilean desert, etc. Okay. I'll tell you just a little bit more about what this technique involves, because it is pretty key to what we can do robustly and what we can't. So it's called very long baseline interferometry because we are using data, signals recorded on disparate parts of the Earth. The telescopes, of course, aren't connected to one another, but they record every incoming waveform with high fidelity. A lot of it is noise, but that's how you get to petabytes of data. And then you take these recorded data, put them on supercomputers, do a step called correlation, basically multiplying the signals to see where they intersect. And at the end of this, what you have is basically every pair of telescope at every instance of time gives you one spatial frequency of the image. The math is identical to when you go for an MRI or a CAT scan, and I hope not everybody had to do that, but the idea there is that the machine rotates around you and keeps on taking X-rays at different viewing angles. And the reason it's called CAT scan is because it's computer-aided tomography. The computer combines these signals and tells you, gives you the three-dimensional structure of what's inside you. Exactly the same math applies to astrometric interferometry, where one pair of telescopes will give you one data point on this image. So we can't rotate it around this contraption around the source, but what we can do is wait for the Earth to rotate, and that gives you different looks at the source. And then, of course, if you have many of these N telescopes and choose two pairs of baselines, start filling out this, what we call the Fourier space, different looks of the at the source. And what you have at the end is a incomplete or a sparse coverage of the Fourier components of whatever source you were looking at. Okay? So we did this starting in 2017 and then most of the years since, other than COVID. And here is the Fourier space coverage from 2017 data of M87, one of our two targets in the Virgo cluster. It's a nearby supermassive black hole. And on the left, all the baseline pairs are color-coded based on which telescope took the data. But if you assume for a second that you're not interested in the two-dimensional image, the azimuthal information, and you say, you know what, I'm just going to combine it all into how big was the baseline and what is the signal that I got, and collect it into a plot like what you're seeing on the right-hand side. This is the Fourier amplitude of each of those pairs. And this is the separation between those pairs in terms of a billion wavelengths, 1.3 millimeters. Okay? What do you see here? Well, you had some high data points here. It took a dive. If there's a ringing, it probably took another dive and then came up again. So even if you know nothing else about this, you can say that this is a ringing function in Fourier space. And people like Jason and I spent inordinate amounts of time looking at Fourier transforms of images. So for people like us, you look at this and you're like, aha, this is a disk or a ring. Like there is just, it's a Bessel function, it's Fourier transform. It's the Fourier transform of a disk-like or a ring-like image. Okay? So let me show you the same for Sagittarius A star. All of the baselines, again, color-coded on the left, collected into one visibility amplitude versus baseline graph on the right. Same thing. it's a ringing function. It's a Bessel function, which tells us, oh my gosh, we have a compact image. Well, how big is this image? And does it have a hole in the center? That's the next level question. So how big is this image turns out to be incredibly easy. Because in Fourier transforms, where that first minimum is, gives you the size of the image, okay? And it was approximately 52 microarc seconds, very much in line with our early predictions of what this would look like. And then the rest you have to model a little bit. We tried many different ways. We did geometric models. I'll just show you one that is very agnostic, which is called regularized maximum likelihood. You take an image, you divide it up into pixels, and again, this is the data that you're trying to fit. So you have a guess. Let's say this is your guess. How does it do in terms of fitting the data? Oh, pretty terrible. So this is the north-south is one of the directions. East-west is the other direction. And you can see that you're not fitting the data. That's fine. You can always say, okay, I'm going to define a chi-squared, but I don't have so many data points that I can independently determine the brightness of each of these pixels. So I'm going to put a penalty based on some regularizing ideas that I have. Okay, so I'll run this forward. As you can see, it is a compact source. It is a ring. The thing that fits is not a solid disk. It's a ring. And it has some asymmetry in the sense that north-south and east-west doesn't look identical. It's more like a little bit more like a crescent than a uniformly bright ring. Okay? We can agree on those, right? Okay, so according to all our modeling, we associate this flux depression at the center, this darkness in the center of the image, with the shadow of the black hole, which I will explain in a second. Especially in M87, not so much inside J star. There's a little bit of a north-south asymmetry. It's because the gas is swirling around the black hole, so coming towards you, it's Doppler boosted. Going away from you, it's a little bit dimmer. So basically, we would look at this and say the angular momentum axis in this image is in this direction, so that the gas at the bottom is coming towards us. And then why is there brightness in the first place, like I showed in that big set of simulations? Well, that's the plasma around the black hole that is shining as it's making its way down to the horizon through this accretion flow. Okay? Any questions so far? Yeah. Yeah. No, it's because you have more degrees of freedom in what you're trying to fit than data points. So you have a small number of data points determined by how many baseline pairs you have. And pixels are n-squared pieces of information that you can't independently constrain. But that's a great question. Thanks for asking. Okay, so let's move on to what we did with these images. We put together the array. We got these images, at least at the 0th order. We can agree that they are rings. And what we are saying is that these are actually rings that are caused by the gas emitting light, and the flux depression at the center has to do with a very unique black hole property that it basically has a point of no return that we call the event horizon that light can't escape from. So a little bit on what we mean by a black hole shadow and how the images form. So assume that this is a this is a black hole. I'm going to mark a few special radii in general relativity around that center, that's the black hole. And this is going to be the line of sight at which we're looking at this thing. So let's say that I integrate it from the horizon here out to infinity. I would call this impact parameter 0, going straight through the center. And as I move this out, you will see that because of general relativistic light bending, it's going to cause self-lensing of the photon paths around itself, and it is going to lead to very interesting phenomena. So these special radii that are marked, this is the photon path, this is the horizon for a Schwarzschild black hole, and this is the photon orbit at 3 gravitational radii. So look at what happens as we change that impact parameter. There are special characteristic impact parameters at which the photon path does a loop-de-loop, or 2 or 3 or 4. Like it can go into the special region where it can have either paths that came from this side of the accretion flow, made it all the way around and out to the observer, or paths that actually got swallowed in. So the red one doesn't make it to the observer. The black one picks up a ton of contribution because it's going all the way around the black hole. And the green one, just a little bit further out, is still being gravitationally lensed by the black hole itself. So the radiation that we see out here is the integration of all of this path. Okay? Now let's put an accretion disk on it and see what that intensity would look like. Again, the black hole is at the center, truncated at the event horizon. This is the photon, the critical photon orbit. And this is one path that went all the way around, so it picked up contribution from here and here, if it came from there. Just a little bit farther out, it picked up contributions from here and here. This one traversed it once, and this one traversed it a little farther out. So just by looking at this, we can say, without knowing a tremendous amount of detail, that we are going to have brightness increasing towards the center because the temperature and magnetic field strength are increasing. It will hit a peak where it's the photon path, and then anything infinitesimally inside of that is going to be sharply suppressed. Okay? That's what leaves this characteristic shadow in the middle, bright ring at the center, and then a gently falling profile outside of it. The details, of course, matter in the sense that we want to know the electron temperature, we want to know the magnetization and magnetic field strength, but as a 0th order, this is how images are made. Now, because we want to test whether the images that we got for M87 and Sagittarius star obey general relativity, we also had to explore alternatives to general relativity and see how images are formed there. And we built in 2021-22 a semi-analytic model that took all of the good parts of the GRMHD without the time variability, put it into alternate spacetimes, and we asked ourselves, okay, if it wasn't GR but something else, what would it look like? What you see here is that this is the Kerr black hole, what I already showed you. This is analytic variations, the JP metric from the Kerr black hole. But if I kept everything else the same about the black hole and just changed its metric, you would see that both the shadow and the ring became larger. We made boson stars where the hole went away completely. And doesn't matter what these alternatives are. But ultimately, if you want to test the theory, you can't just do what would that look like and compare it to the observation. it's best if you can also explore what the alternatives would look like and say it is not that and it is this, right? Because if the predictions of all these theories was identical, then you don't have a discerning diagnostic. So one caveat here is that what we want to test is what is the size of the shadow. What the metric, the space-time of the black hole tells us is how big that shadow should be. But what we are seeing is the light. So we wanted to see how closely does the light trace the shadow of the black hole in order to be able to use this for a test of general relativity. So I think I already mentioned that we did this for different metrics. We did it for different black hole spins, observer's inclination, and many different accretion flow models. And we asked ourselves, if I see this ring and I can measure the size of that ring, what does the theory tell me the size of the shadow is? Okay? And that's a calibration factor. And because we don't know what it is, we had to do this for all of these models. The good news is that the spread in this calibration factor was very small, even for non-Kerr models. And whatever we did to the plasma within reason, like we didn't say, what if mass conservation is not observed? Like we didn't do that. But anything short of that, we tried to do it. We made hot electrons, colder electrons. We made spinning black holes, non-spinning black holes, etc. And we defined this calibration parameter in the synthetic image set as what we're measuring as the diameter of the image over the diameter of the shadow. And here's what we found. These are the histograms that show this fractional diameter difference, so that calibration parameter -1, for different sets of either full GRMHD or analytic Kerr or analytic non-Kerr. And what you're seeing is that there is a very strong peak at about 10% difference, so at 1.1. The ring, is always a little bit bigger by this amount. But whatever it is, it's a calibration factor. You can measure this distribution, you can quantify it, and you can use it to do whatever you're doing to your data, the same thing to your models, and say, okay, if this is my ring size, what is the shadow size? And then the next point is this consistent with what general relativity is predicting for a black hole of this mass? I understand Andrea Ghez was here last week and gave an excellent talk on how we measure black hole masses, especially for the one at the center of our galaxy, Sagittarius A star. And that's another 20 years of work that gives us an independent measure of the mass of that black hole. So if I know that, I know its shadow size. If I know the shadow size, I can calibrate it to the ring size. Then from the EHD, I have a ring size measurement. It's a very simple question to say, do these match? Okay? So that's what we did. The measurement on the left, the prediction on the right, and this is the deviation parameter. If delta is 0, it means it is what GR predicts. If delta is non-zero, there's a discrepancy between the measurement and what I expect for the ring size of a GR black hole that is at the mass of Sagittarius A star, or M87. Sag A stars uncertainties are much, much smaller. That's why I'm showing that here. Forget about what these mean. There are all sorts of different ways in which we did this. And why is there a purple band here? Well, one thing we don't know is the black hole spin. So there is a small, it's about a plus or minus 3% uncertainty. So what I put here, 6 square root of 3 is the Schwarzschild prediction, so non-rotating black hole. But if it is rotating, it could be anywhere in here, and this is where our likelihoods peaked for that deviation parameter delta. Okay? So, good news, GR worked. Bad news, GR worked. Like, we did this like 20-year experiment to see some sort of a deviation because we think that there might be some clues very close to the horizons of black holes that could guide our efforts into what might be incomplete about gravity. This ain't it, okay? So, okay. So before I move on to, I told you the good things about the models that we trusted to make this measurement. What are the things that weren't as successful? I'll take questions. Yeah.
We have a figure where we show that the photon is that four constant? Okay. You're saying that if you add spin, if GR works, it only corrects the size of the photon?
Exactly. So that's the part that I skipped here. This D shadow is also calculated for the particular mass spin combo in GR or mass spin deviation parameter combo if it's not GR. And that's how we had derived with my former student C.K. Chan analytic approximation for D shadow for Kerr black holes, and we used that. And for non-Kerr, we numerically measured it. Yes, but the good thing is that it moves in tandem with the photon ring. So the calibration is unaffected, but the absolute value of the size is affected.
Okay.
Other questions? Okay, so you believe this GR test. Excellent. Let's move on. Okay, so where are the models inadequate? Well, I already told you there's a lot that we don't know. We can't connect the feeding scales of black holes to plasma scales. Like Dmitry Uzdensky here is an expert on how energy is dissipated at the scales of the electrons and how they gain energy as a function of all the turbulence that's happening or the reconnection events of the magnetic fields that are happening. So we know that there's a lot of physics that we're missing, and we've been working on this in parallel for many years. But one thing that we saw from the data itself is what we named the variability crisis. So here is a typical light curve, flux at 1.3 millimeters as a function of time in hours that we made from our large library of simulations for Sagittarius A star. It is a relatively small mass black hole. It's only 4 million solar masses, which, believe it or not, for supermassive black holes, it's pretty puny. So the dynamical time scale around it is short. So we thought, yes, it's going to vary as the turbulent flow goes around the black hole at the dynamical time scale. We're going to see these large variations in the flux that we observe from the source. In fact, we were worried about this as we were reconstructing our data to see, like, worried about how it could affect our images. This is not a particularly noisy simulation that I'm showing you. In fact, it's not one of the noisy ones at all. So when we saw the actual data, that's represented in this band. The variability in the flux is represented in this green band here. Let me show you in a little bit more detail what those data look like. This is actual observing days in 2017, April 5, 6, 7, and 10. There is a flare here, which we think is an episodic energetic event. Not counting that, it kind of came back to those levels. So the mean variability here is much less than the mean variability here. What that suggests to us is that we are capturing the basics of the accretion flow, but how the turbulence develops, what happens in the inner region, etc. Maybe we're missing some things. And probably one of the key physics ingredients that we are missing is again, how electrons are heated, because the only thing we see is the light emitted by those electrons. So we might get the big picture right, but unless you can tell with certainty how electrons are heated, you translate it into a signal that might be too variable or a little different. So yeah, I think I already said this. They lack the physics, the MHD simulations themselves, to reproduce this flare, but overall in steady state, they show too much variability. Coming back to this separation of scales problem, even if we forget about the feeding scale and just look at the scales at which we can typically represent in these GRMHD simulations. This is the wave number, so 1 over the length. The smaller it is, the larger the length scale. So going from left to right, we're going to look at smaller and smaller scales. This is what GRMHD simulations capture. We also do a type of simulation called a shearing box, which means that we take a little segment of this accretion flow. It could be in Keplerian rotation, so there's a little bit of a shear in the outer and inner parts. It could be some other angular momentum profile. And we again set up these equations. We can get down to smaller scales, but not much smaller. So we do this shearing box simulations. And then what we anticipate, theory tells us, is that there is a regime of wave numbers going from this scale at which plasma is excited, the slow and fast magnetosonic waves and the alpha N waves are excited, and they cascade, this power cascades down to the smaller scales. And then there is, for ions, there's Landau damping that dissipates and heats the ions, and it continues. The electron heating scales is even further down. And depending on the conditions of the plasma, we would get a different ratio of the energy going into the ions and the electrons in this ionized plasma. I know this is a lot. A lot of you haven't taken plasma physics, but this is what you have to deal with if you're doing astrophysics of these types of objects. So this is from a recent paper from our group. I think he came and visited not too long ago, so some of you met Kaushik. And this is the particle in cell, or the PIC scale, at which we can do this extremely well, but it's limited in terms of, again, they're very expensive simulations. So assuming some things about the environment, you can look at that dissipation, but you can't connect it all the way back out to accretion flow scales. With Kaushik, building on some of the work by Kawazura and collaborators, what we saw is that the electron heating to total heating ratio, so QE over QI plus QE, has a particular dependence on what we call the plasma beta, which is the ratio of the thermal energy to the magnetic energy in the flow. That tells you, for example, what is the temperature of the ions versus versus the magnetic energy. So there were some simulations, or actually there was analytic work, gyrokinetic work, that showed that the compressive to alphane ratio of how the energy is partitioned in the turbulence in the accretion flow drives this heating ratio. So this is the original work from House et al., who took only alphane waves, and Kawazura extended it to alphane plus what they call compressive. It's really the slow waves. And so we built on this work to actually calculate some of the heating ratios. And we took it a step further, and we actually looked at what physics sets this partition between the energy injected into the slow waves versus the Alfvén waves in the accretion flow as a function of the plasma beta again, which is shown here. But this is a result of shearing box simulations where we also controlled the shear rate, because that drives, this is for the experts, this is only for MRI-driven turbulence. For the rest, doesn't really matter. But 1.5 is the Keplerian shear here. But we also thought, because off the mid-plane, you can have the shear rates that are different than Keplerian. So we connected this injection of slow to Alfvén power ratio to shear and a small dependence on the plasma beta parameter. Why is this important? You're going to say, well, you were just guessing what the electron temperature was like. Why is this going to be a step forward? Well, now we are able to connect how accretion is driven in the first place, why accretion happens, how turbulence develops, to how this power cascades down to small scales, and which of those waves couple to the ions, which of those waves couple to the electrons, and how this partition leads to a heating ratio. So it's at least a step forward in terms of understanding what this heating ratio is, again, as a function of shear and plasma beta. This is typically the range that we encounter in accretion flow simulations, and we are able to understand how much heat is given to these different species in steady state. This doesn't have reconnection in it. Reconnection would be another way of heating it, but this would be the steady state. Yeah. Total plasma beta. Okay, so once you understand how much heat is pumped in, you can then say, okay, then what's the temperature ratio? And for that to go from the plot on the left to the right, Koshik also developed a model where there is compressive heating, there is this heating, this turbulent heating, there is electron cooling, and calculated what these temperature ratios are like. So these are now the ion to electron temperature ratio that we use in our simulations as a function of the plasma conditions and as a function of shear. So at least at this point, post our first set of EHT results, we have a more predictive model of what the electron temperatures should be like that we can use as a subgrid model for the GRMHD simulations. And then we can ask ourselves, how is variability affected? How are images affected, etc. So the takeaways from this part is that GRMHD models get the main features right. We've tested it extensively by doing parameter surveys, and we've tested it extensively against the data. The main features being the scaling of the main features of the images, etc. But by definition, they can't capture the dissipative processes happening at the smaller scales. And our recent effort has been focused on what this electron and ion heating should be in MRI-driven turbulence. And going forward, we will see, for example, if this changes the variability that we predict from the models and how it impacts other characteristics, observed characteristics of accretion flows. In the last 2 minutes, I'm going to tell you, I'm going to skip that, about a machine learning effort that we've embarked on based on this literally tens of thousands of simulated images that we call PRIMO. I already showed you the regularized maximum likelihood method that divides the image up into pixels and says, does this fit the data modulo some regularizer conditions? The problem with that is based on the regularizer that you apply, you get a different answer. For example, the 3 bright spots on the Sagittarius star image are most likely artifacts of what we assume in order to complete the sparse data. They are not, we don't think, they could be, there are ways in which you could have bright spots on a black hole image, but we don't think those particular ones are, because even when we have smooth images and apply our methods, oftentimes we get those spots. So what did we do? We said, okay, let's build a basis for reconstructing these images that we use the GRMHD library and its images as the training set for how we're going to reconstruct the images. And you might think, well, maybe that bakes in what you know or what you anticipate about the images into the images that you will get. But that's not the case. The reason is that we're just using this as a basis set on which we can, from which we can reconstruct black hole images. So I'll just walk you through the steps. This is the library. And what we're trying to build is an orthogonal eigenbasis for the space of images that can exist. So we take this, we do dictionary learning methods. It's not deep learning. And we build on the set. You take a snapshot and you say, using this eigenbasis, first you filter it to the resolution of the EHT because we don't have infinite resolution. And then you say, just like building any function out of a Fourier basis or out of Legendre polynomials or out of Laguerre polynomials, for different problems, you choose a basis set that minimizes the number of components that you need to use to build that function. So all we're saying is, let's use a smart basis set that we learned from the GRMHD simulations and ask ourselves, with a minimum number of components for anything that we want to reconstruct, are we able to do it? And in this, we also included images that are not ring-like to make sure that our basis actually is general enough to serve this purpose. So this is with 3 projections. This is with 20 projections. It's getting pretty good. And this is with 40 projections. Okay? This is not real data. This is an example snapshot that is not part of the training library. So you build your basis set from a training library, then you take a snapshot that didn't belong in there and say, reconstruct it with those for me. So based on this, we settled on 20 components to get to the features that we can see in EHD resolution. And the reason that this works is that why is this an optimal basis set? Because it learns the correlations, the algorithm learns the correlations in that Fourier basis on all sorts of images, how they look basically in that visibility amplitude versus baseline length space that I told you about. So using this, we were able to improve M87's reconstruction. This is the original 2019 image from the regularized maximum likelihood methods. This is the raw primo reconstruction, but this has information that EHT can't access because of its finite resolution. So this is the image that you should look at the EHD resolution using that more optimal basis. That's what the image looks like. It fits all the available data. It doesn't make any prediction about the wavelength or the wave numbers where we don't have data. And it basically just uses the full resolution of the array and better physics constraints in order to enable this image. So hopefully I've given you a sense of how the theoretical and computational work helped guide the array, what we were able to do with it in terms of GR tests, what we know we're missing, and we're collectively working on as a community to improve those. But in the meantime, there are very nice additional benefits, like this machine learning algorithm that we can develop from those extensive simulation efforts. And going forward, hopefully, we'll do it for Sag star and multi-frequency images in the future as well. So I'll stop there. Thank you.
Does it shift your analysis, your analysis, if you include magnetic structure prior?
Magnetic structures as priors are only coming in through this simulation library, which has a lot of different magnetic structures. So the training set already has them, but as a particular constraint that we are imposing on it, beyond that, we haven't looked at.
Is it possible to do it, given like the magnetic information that we have?
Absolutely. We could do it for, we could, I mean, this is still agnostic enough in the sense that, you know, as long as you give me a complete orthonormal basis, I will reconstruct it. If we looked at only a subset where we think we know the magnetic field geometry or some other information and reconstruct it from that, it's a good question. I don't know if it would shift the final answer or not.
I guess I'm just trying to understand to when we actually try to develop a new position. What is defining HPE from a perspective? Is it just each one's different simulations?
That actually just comes from PCA. So when you do a principal component analysis and you look at the variation of, for any set of images, each component, each eigen image, eigenvector that you get from PCA is guaranteed to be orthogonal to the other one. So it subtracts that component. So just like you do in basic like eigenvector analysis, PCA has that quality as well.
What is the next result comparing them between? Yes, that's
It is certainly one of the goals. I mean, this is really like one person's trash is the other man's treasure. So either you say the plasma is a nuisance and I just want GR constraints and I'm going to do whatever it takes to get there, or you say this is an amazing opportunity to learn about the accretion flow and the plasma. What can I learn about it? I don't feel comfortable at this point, like having seen all of the work from the collaboration, to say we learned this versus that. For example, we published papers that say MAD type of magnetic field initial conditions are preferred over the same type of magnetic field initial conditions. There is some truth to that, but I think that's also impacted by some of the particular data comparison.